Hello everyone, welcome back to BC Calculus. Today we're going to talk about lesson number 25, which is how to solve differential equations, and we're going to also incorporate slope fields in this. So right here on the notes for differential equations gives you guys a general idea of what you have to do. What is a differential equation? A differential equation is an equation that actually has a derivative in it. So dy dx is equal to, or it's somewhere in there, a derivative is part of the equation. So that's simply what, for our purposes of what we're going to do in BC Calculus, we're going to just understand it as that. There's a lot of differential equations. There's a whole course on differential equations, but in layman's terms, it's really an equation that has a differential equation in it. We're going to really focus in this course on first order differential equations. And so what we want to do here is we want to solve for it. We want to get rid of the dy dx. We want to basically find a way to get an equation which is equal to y. So we want to basically go backwards with y. One of the things that we're going to end up doing in solving differential equations is something called separation of variables, which is what the actual unit is called, the 8.2. It's separation of variables. So let's actually just go down here and show you an example of how to solve a differential equation. So we actually already have the steps over here. So in this video, I'm going to show you guys just kind of the idea of how to solve a differential equation, given the fact that this is already solved for us, pretty much. And then we're going to go ahead and do a couple of examples where we're going to solve a differential equation and then talk about a particular solution. So you guys can see here that we have dy dx is equal to 2x over y. And so again, it's a differential equation because dy dx is part of the equation. So the first thing that we want to do is we want to separate the variables. And so this is going to be, and there's no proofs for this. This is just kind of like a little notes for it. So we want to separate the variables. We want to separate the variables. So what does that mean? What does it mean to separate the variables? We want all the x's on one side, all the y's on the other. And for the purposes of this class, especially for the first couple of videos, this is going to be very easy to do. Most of the time, it's cross multiplication, right? So let's multiply both sides by y, multiply by dx, and we're going to get that. And so this step right here, we just need to add a little bit more. So they showed by multiplying both sides by y, but we also want to get the x on the other side. So we're going to go ahead and multiply both sides by dx, and we're going to get this. So now this is truly separation of variables. And usually sometimes they actually give you guys a point on the exam for actually just simply separating the variables. I do want to say that this note set, I'm just not a big fan of that because we don't really need this step because we've already did this particular part right here. So we're going to jump down to right here. So once you do this, we need to get rid of the dy and the dx. So what's a very easy way for us to do that is actually integrate both sides. All right, so we want to integrate both sides. And this is why it's really important that we separate our variables, because now we're going to integrate the right side with respect to x, and we're going to integrate the left side with respect to y. And so both d and e are the same step, right? So we want to add the integrals to both sides, right? So we add the integrals here. So this is where we actually added the integrals. Again, I'm so sorry for my handwriting. So add the integrals to both sides, and then we want to then simply integrate. So integrate y, we get 1/2 y squared. We integrate 2x, we get x squared plus c. And then what we would do to actually finish this question up, if we wanted to actually solve this, and this is actually a legit answer, but we could go a little bit further with it if we wanted to, and we could multiply both sides by 2. And again, I'm going to do a couple of examples with you guys. Well, lots of examples in these videos, but go ahead and multiply both sides by 2. And I'm going to talk about this c part in a further example. But yeah, so we get y squared equals to 2, so we multiply everything by 2, 2x squared plus 2c1, or just c, it doesn't really matter. I'll go ahead and talk to you guys about why it's c1 in a minute. And then your final answer, if you wanted to choose to do this, would be plus or minus the square root of 2x squared plus 2c. And this actually could just end up being another c, which we'll get to in the later thing. But that's the steps for differential equations. So let's go ahead and solve one. And in example number 2, it's actually given this initial condition. So let's actually go ahead and do this. And the first thing we're going to do here is we're going to separate our variables. And we're going to move the y to the left side by dividing by it. and then we're going to cross multiply here, and we're going to move the x to the top. All right, cross multiply. So the y comes down here, the dx comes up here. So there's our separation of variables. dy with the y, x with the dx. And now we're going to add our integrals. When you're doing differential equations, you definitely want to show this step. You definitely want to show that step. And then you want to do these problems separately. So you want to treat them as two completely different problems initially. So if I integrate x, this is just going to be x squared over 2, or 1/2 x squared, right, plus c. And if I integrate the left side, then I'm going to have 1 over y dy, which you guys know from previous lessons, that's going to be the natural log of the absolute value of y plus c. And so this is where, you can have a c1 right here and a c2 right here. But I want you guys to understand that if I remove, and these c's, they do not have to be the same values, so please don't think that they cancel out. But my point that I'm making here is that if I were to subtract c from this side, I get c1 minus c2. So let's call this a c1, just so we're clear that these are two different constants. And I'm not going to spend too much time on this because this always works. If you subtract c1 from c2, you just get another value c. You get another value c. So what I essentially could just say here, and this is what I'm going to do for every single problem from the rest of it, is I'm going to go ahead and just have this right side with the x is just a c. And so this is just, again, the c is just the difference of c1 and c2. But you don't have to clarify that. So I just kind of integrate this without the plus c, and then here I do the plus c. And now, ladies and gentlemen, we have to solve for y. We have to solve for y. So what do we have to do? Well, in order to get y by itself, when we have a natural log, is we have to raise everything to the e power. So is this the best, probably first example for me to show you for differential equations? Probably not. Probably not, but I probably should have showed you an easier example than this, but why not start with something more challenging, right? And then go to something more basic. But yeah, that's what this is. So in order to get, the natural log of y out, then you want to raise everything to the e power. And so this right here, e to the natural log of anything, is that thing. So then this is just going to be the absolute value of y is equal to. And then I'm going to go ahead and do e to the 1/2 x squared. And then you guys hopefully remember that there's actually a property that e to the a plus b is really a to the a times e to the b, right? Power of exponents for this. And so we get an expression here that we get y, and because e is always positive, I can essentially actually drop my y now, the absolute value of y, and I can get this right here as e to the 1/2 x squared times, and again, this is another constant. So we're going to leave it right now as e to the c. All right, but again, eventually in this lesson, we're going to talk a little bit more about that. But this is our solution. This is the solution to this differential equation where y is equal to e to the 1/2 x squared times e to the c power. And again, this is just a constant as well. So all these constants with this. It's asking us in part B to find a solution, find a particular solution that satisfies the initial condition y equals 0 equals 2. All right, so I want to tell you guys that when we're doing this particular kind of problem, the best thing to do is, and this is just a strategy that I personally want to say, is right here. So once I've integrated both sides, once it's completely integrated for both sides, I plug in right there because I don't want to get more complicated because it's so much easier right now to find the natural log of y, which again would be the natural log of 2, much more simple than to go through all of the song and dance and then get it at the very end. So if I find the initial condition, I'm going to go ahead, and this tells us what our c is immediately. This tells us exactly what our c is. So if I can say the natural log of y, which is going to be the natural log of 2, based on right here, it's going to be 1/2 x, well, x is 0, squared plus c. This lets me know that c is equal to the natural log of 2. The reason why I like to do it here is because then anytime I apply something, I already know what the value is going to be. So let me show you guys what I mean by that. So now I know that c is going to be the natural log of 2. So then I can say y is equal to e to the 1/2 x squared times e to the natural log of 2, right? It's just right there. I could put it plus natural log of 2, I could put the natural log of 2, whatever it is, and this is just going to equal 2. So I know my particular solution for this is going to be 2e to the 1/2 x squared. So now I have a particular solution to this differential equation. And there we go. So there's our first example. Again, I apologize, I chose a little bit more complicated problem. So example 3, hopefully it's going to be easier than this one. But it was still pretty good. It's still pretty easy to do. But that's the idea of what's going on in the differential equation. I think this would be a good stopping point for this one, and then I'll come back and do a couple more differential equations for you guys. And then we'll do some applications, and then we'll finish with slope fields. So I'll see you guys in the next video.